In the math talk where I developed the derivative of the inverse cotangent function, I promised that we would do a really cool application that uses that function. And here's what it looks like. We have a movie theater screen that is set up so that the bottom of the screen is A units above eye level, and the top of the screen is B units above eye level. Now, we're trying to figure out at what distance x should a viewer position himself so as to maximize his angle of view theta. So in my diagram, I have my movie screen in orange, and I've got the bottom of the screen being A units high and the distance to the top of that screen being B units high. And I've positioned myself along this line that is perpendicular to the screen, and I'm trying to figure out if there is an optimal location x or an optimal distance x so that my angle, my view angle tucked in here, theta, is as large as possible. Now you might think that maybe that doesn't change as you move in and out, but I think if you were to picture being positioned further away or being positioned closer, you'd see that in fact that angle does change. Now, without just accepting what I've said there, let's look at it graphically just to confirm that we have a change in that angle as x changes. So in the graphing software, I've set it up such that the bottom of the screen is 5 units high and the top of the screen is 20 units high. Again, I just arbitrarily picked those numbers, and I'm starting the viewing location out at 50 units. Now, what we're going to do is allow that value to change. I'm going to change that value, and up here we're going to track two things. The x-coordinate up here will track the position, and the y-coordinate will track the size of the angle in here. This number here is computing the size of this angle. So we'll let that distance shrink and see what happens to this y-coordinate. Here we go. You can see that as the person moves closer to the screen, the size of that angle increases and increases. And it does it to a point, but then it starts to round off, hit a maximum value, and then start to decline again. And so you can see here that if we get too close to the screen, the size of the angle tucked in here starts to shrink, and there seems to be some sort of optimal distance where that angle gets as large as possible. Anything before that, we can improve by moving closer. Then we get to a point where moving any closer actually takes away from the size of that angle. So there is some sort of optimal value for our distance, and we'd like to see if there is some sort of relationship between that distance and these two dimensions, the height of the bottom of the screen and the height of the top of the screen. So that's what we're going to try and find a connection to when we go back and solve our problem. Now, returning to our problem, we're just trying to determine the optimal distance x in terms of the A and B screen dimensions that will produce the best value for theta. In other words, the largest value or the most immersive viewing angle that you can get. Now, with that, we recognize that a way to describe angle theta is to use angle beta, which is the acute angle in this large right triangle, and angle alpha, which is an acute angle in this smaller right triangle, and say that theta is in fact beta subtract alpha. Now, beta is related to the screen dimensions and this distance x in the following way. We say that x is the adjacent to angle beta, and b is the opposite to angle beta, and so we'd say the cotangent of beta is x over b. And what follows from that is the statement that beta is the cotan inverse of x over b. By exactly the same argument, we can say that cotangent of alpha is x over a using the smaller triangle, and alpha is cotan inverse of x over a. Now we can write the expression theta equals beta minus alpha and replace beta and alpha with their cotan inverse expressions. Now, at this point, we've got theta depending entirely on x. A and b are just the particulars of the screen that we're using. So as I change x, I can manipulate theta. And we know from calculus that if we want to try and maximize a function value, we set its derivative equal to 0 to create a horizontal tangent line. And then we have potential for a max or a min value. Now, if you have not gone through the inverse cotangent derivative tutorial that I did earlier, I really strongly recommend it at this point because it will be difficult to follow along with the algebra from this point forward if you haven't seen that. And if you have seen it and you want to try and take this on your own, I would pause the video and try and take the derivative and set it equal to 0 on your own and see if it matches what I get. Now, that derivative from the previous video, we specifically took the derivative of this expression, and we got d by dx of cotan inverse of x over a being negative a divided by a squared plus x squared. So using that structure, we differentiate the first inverse cotangent, and we will get negative b over b squared plus x squared. And the second inverse cotangent will differentiate to produce minus negative a over a squared plus x squared. Now, simplifying by distributing this subtraction sign into the brackets, we get simply that d theta by dx is negative b over b squared plus x squared plus a over a squared plus x squared. At this point, like any optimization question that you do in calculus, we're going to set that derivative equal to 0. So on the left side we have 0, and on the right side we still have the same expression. Now, to make it easier to solve for our x, I'm going to add to both sides the b over b squared plus x squared term, so that here and here, these two will subtract out, leaving us simply with the expression b over b squared plus x squared equals a over a squared plus x squared. The next little bit of algebra just involves a process that people sometimes call cross multiplication. It's really just a statement that if you have a over b equaling c over d, a times d, this product, is equal to b times c, this product. So I'm going to take the b and multiply it with this denominator, and the a and multiply it with this denominator to produce b times a squared plus x squared equaling a times b squared plus x squared. Next I'm going to expand, so I get a squared b plus b times x squared, which is bx squared, equaling ab squared plus ax squared. Now at this point I'm almost ready to isolate x. All I need to do is gather the x squared terms to the left-hand side of the equation and everything else to the right-hand side. So I will write b squared x squared, subtract my ax squared, equals ab squared, subtract a squared b. Now on the left-hand side I have a common factor of x squared, so I will factor that out, leaving behind b subtract a. On the right-hand side I have a common factor of ab. I will factor that out of both terms, leaving behind b subtract a again. Now at this point, I can simplify both sides by dividing through by b minus a. And I'm okay to do that so long as b subtract a is non-zero. And I know from the problem that I'm dealing with, a and b are not going to be equal to each other, otherwise we don't have a screen. So I know that this is going to be a non-zero quantity, so I'm safe to divide out on both sides. And it leaves me with an incredibly simple expression that x squared is just the product of a and b, or x itself will be the square root of ab, and I'm only taking the positive case because we're dealing with positive values in this problem. And so this, what looked to be a pretty complicated question, has come down to a really simple and almost elegant answer of x being the square root of a times b. And for some of you, you might recognize that as what we call the geometric mean between two numbers. In the graphing software, I had a equaling 5 and b equaling 20. Well, inserting those values into our final expression, I get that x is equal to the square root of 5 meters times 20 meters. X is equal to 100 meters squared, square rooted. X is just 10 meters. Now, returning to the graphing software, we can see that the distance of 10 meters matches exactly what we got in the software. Now, adding a circle that circumscribes the purple triangle, we discovered that our optimal distance matches a circle of minimum radius. Now, I'm not going to tell you exactly why that is. I'm just going to say it's connected to central angles and inscribed angles in circles, and it would be great if you left your thoughts in the comments section as to why you think that might be true. In any event, I hope this changes where you decide to sit in a movie theater. Thanks for listening, and we'll see you in the next video.